Okay, we are live. As usual, we switch to English. And well, in this tutorial, we'll be talking about the relationship between the orthogonal projections and a very common problem, that is the least squares problem. We have already seen it only as a way to solve linear systems with a non-square matrix, or a matrix without a full rank. But we'll be looking at it in another angle this TA. Then after that, I'll be relating the least squares problem with denoising, or at least a very basic way of describing a denoiser. And then I'll talk a little bit about filters and how to clean a signal. That is a thing that is very common in signal processing and in general. Okay, so let's start with the orthogonal projection. As you can see here, basically the orthogonal projection, or the orthogonal projector operator, the one that you saw on class as P sub V, being V the subspace. Here I'm only doing it in a vector X. And basically, if you have Y and you're going to get the orthogonal projection onto this vector X, what you're trying to achieve is to find a vector P, that is the projection, that satisfies that this vector in yellow is orthogonal with P. The vector in yellow is Y minus P. And this is something that is basic for engineers, but I'll be talking about it a little bit more. Y, if I have, for example, a vector X and a vector Y, what is this vector, for example? If I wanted to have this vector, what is it? X minus Y, Y minus X, Y minus X squared. Which one is it?
The last one?
The last one with the square? No, it's not that one. That one was a joke. Basically, our contestants are X minus Y and Y minus X. It seems like a very basic question, but it's not as basic if you don't know the answer immediately. So basically, let's start with an example. If you have a coordinate system, here X, here Y, and you have a point, for example, just to make it easier, 1, 0, denoted by this vector, and you have another one here, just to make it very easy, 0, 1, and we wanted to get this vector. A vector is a representation of a coordinate that I'm putting it here, but obviously this vector is the same as this one. Right? It's the same vector. I just draw it in a different position, but it's the same one. It would be described by the same components, right? So obviously, this vector here should be minus 1, 1, pointing in that direction. right? So that means that if this is our vector y, this, now let me put a different name, x1 and x2, and this one is y. We have that y equals to what minus 1? What? x1 minus x2. Do you see this? So here, just by visual analysis, this vector is the same as this one, and because our example is very easy, we can obtain the coordinates minus 1 in the x-axis and 1 in the y-axis, obtaining minus 1, 1. And there's two possible combinations, this one minus this one, or the other way around. And obviously, to get the minus sign, we need to subtract x2. That means that is x1 minus x2. That is something that is not obvious at first, so that's why I'm showing it here. And basically, to obtain any vector like this one, in this case, we need to have here the end of the vector, and here the beginning. So in this case, if we want to obtain the arrow pointing from y to x, the only correct solution is x minus 1, minus y, sorry. So this one is incorrect. If instead we would want to obtain the vector pointing the other way around, then this is y minus x. This is x minus 1, y. Okay, so this is a little bit of an introduction to the vector addition and subtraction, and how to interpret a vector that is going from one to the other one, because the arrow matter. Okay. Now, before continuing, any question about this? If not, we will continue. Let me see the chat. Oh, a lot of messages. Sorry. Clear. Okay, so if now we want to have this P, and we saw earlier that we have this y minus P. That is because the end of this vector is y and the beginning is P. We put it in yellow. This is the vector y minus P. But in this case, it would not matter if it was pointing in this way or the other way around, because we only care about the dot product. If we do the dot product between y minus P and x, or P in this case, well, with P and x would also be satisfied. So with P, it would be 0, but also if we did it with x, because they are pointing in the same direction. Okay, so this vector was the one pointing upwards, but if it was pointing the other way around, we can see very quickly that that would be the same as multiplying this by minus 1, and the dot product is linear in the second argument. So you can take this -1 sign, put it at the beginning of the dot product, and if we then divide it by -1, we obtain 0 as well. Sorry, in the recording this yellow color is not very good for visibility, so I'll change it to another one. This one. Yeah, this one is better. Like so. Okay, so how can we obtain this vector p? Do you remember? Here I have a confused emoji.
It was the inner product of the vector we want to project with the first vector of the basis, divided by the norm of the first vector of the basis, multiplied by the first vector of the basis, and then you sum the same expression with all the vector of the basis.
Exactly. So that is because we have y is the same as, obviously, y minus p. That is the vector in pink plus p, right? If we do the inner product in both sides by the vector x, we obtain that we have x, comma, y, and by definition the dot product between x and y minus p is 0, so this part disappears. That means this is also called the residual. The residual is orthogonal to the space. That means that you'll have a 0 here, and then you'll add p that, and okay, so this is also important because you can relate the orthogonal projection with the regular vector and they'll be the same, but this was not the proof of the formula. The formula was about writing p. This is the proof of the normal equations. Sorry, I got a little bit confused, but this is also useful. So if you have p and write it as alpha times the vector x plus some residual, the residual is y minus p, no, sorry, I'm mixing things up. That should be the case. Okay, so now p, if we write it as alpha times x and we put it here, we'll have that this is this, so we can therefore see that alpha is equal to x comma y, x comma x. Yeah, I was missing a step, sorry. These are called the normal equations. Then, because P is the orthogonal projection, we can write it as a scaling of the vector x. This is a scaling of the vector x. And if we substitute here, we obtain that the coefficient is this one. Okay, so that means that finally a vector P equals to P is the projection onto x of the vector y.
Carlos, in the homework they asked us like to a very similar question, and do we have to prove it, or is it okay just to write the formula of the projection?
Let me see the question. I don't have the homework here, but can you?
I remember it was like, what is the projection of the vector on the basis? Or
oh yes,
yes.
You use the same theory here, but in the homework you do it with a space. So we will talk about that now. So this is only to project a vector onto another vector. But what if we have a space?
Yeah, but my question is, do we have to demonstrate it, to prove it, or is it okay just to?
Oh no, you can only you can use it.
Okay.
It's knowledge that you already have, so you can use it. Okay. Now I have a question for you. Do the colors help, or they are distracting?
No, they work fine.
Okay. I think, at least for me, it's a little bit easier to do the comparison between the formulas and the vector if they have the same color. Okay, so that's the projection of a vector onto another vector. In the homework, basically what happens is this case here. That is, you have a vector y, but you want to project it not into a vector, but into a space V. And the space V is described by the basis of the vector space. There are V1, V2 until Vn. So you're basically projecting a vector onto a hyperplane, or something a little more complicated than that, but that is a very easy example to imagine. So what happens now? For the projection onto a space V. Do you remember this from class? You have a space V. You have some vectors V1 and V2 that are the bases of this. So V is the span of the vectors V1 and V2 in this case, but it could be more, obviously, more vectors. And we have y, and we want to get this P that is the orthogonal projection, but to the space, not just a line. How can we do it?
So I think P could be a linear combination of vector v1 and v2.
Yes, that's true. The span is the same as all the linear combinations between v1 and v2. So yes, V, the vector space, is a linear combination of v1 and v2. Maybe to see it better, we can have the vectors v1 and v2 here. We have y, and if we do this, like the shadow, we have a component here and a component here. Everything here will be in the space V. So how can we obtain y on this space V? Obviously, to be contained onto the vector space V, that means that y, or at least P, the orthogonal projection, needs to be written as a linear combination of v1 and v2. That's correct. So you have alpha v1 plus beta v2. Can we do something similar to the simpler case here to obtain the coefficients?
Calculate the projection of P onto V1 and then onto V2. And so the partial projection of the coefficients of each one of the vectors.
Exactly. So here I didn't wrote it, but an assumption here is that V1 and V2 are perpendicular. So that makes it very easy. If they are perpendicular, the projection or the dot product of V1 and V2 is equal to 0, right? Now, if we apply the same principle and we do it with V1 first, V1 V1, we have in the left hand side V1 and P equals 2 alpha times beta times V1 and V1, and here V1 and V2. As V1 and V2 are orthogonal to each other, this cancels out. That means that we can obtain the coefficient alpha by writing the projection here, V1, V1, V1. We can do exactly the same, but with the vector v2, and obtain this. Sorry, here I wrote P, but we are interested in Y. This is Y. This is also correct for P. but we are more interested in y. So let me put this a little bit around here. And the same as before, we will have this residual vector. Now I'll just call it R. That has the very special property that is orthogonal to the space. So R and dot product between any of these is equal to 0. So now everything remains the same, but we need to consider R to write things with respect to y instead of p. This is y, this is y. Okay, now have and just to be clear, this part here, it's p. So basically y is p plus r. We're trying to get the coefficients of p. And I wrote p again here. This is y. Sorry, there's a lot of letters and it's a little bit easy to write the incorrect one. Y. There. So after all that, we can write p as these expressions. I can copy paste them. This in the direction b1 plus sorry, I copied incorrect. This one is the term with v2 because it has the v2s there. v2. So this one is here. And now we have the one with v1. b1. Okay. Is it more clear how to obtain the projection of a vector to a vector space now that you have seen the procedure? That was a question. I didn't say it like a question, but it was. Yes? Okay, another last thing, just to correlate this formula with the drawing. This part here, we can write it as a vector x1. No, let's put it as p1. This one here. I forgot the plus sign here. Plus. Can be written as p2, for example. So basically what we are saying is that p can be written as a vector p1 plus p2. Here in this drawing, it gives the impression that p2 and b2 are the same, but they are not. They could be totally different vectors. And the same with another. For example, b1 could be this one. And the same with this is b2. b2 and the same with b1. They're not the same as p1 and p2 that I I'm drawing here. One. There. Okay. Are you following me? Everyone is understanding?
Carlos, I have a question.
Yes.
Um, I, I, I think I didn't get why the vector r doesn't appear in this relationship to get the
Okay,
alpha and beta.
that's a good question. I kind of did it very fast and I skipped a step. This vector r, when you do the inner product with v, it also appears here, right? R, but it has the property that the residual, or r, is orthogonal to the space, because it's exactly what is lacking. So that's why it's orthogonal to the space. That means that this inner product is 0 as well. So that's why it does not appear.
Okay, but it means also that we don't need to use another coefficient there, because in
Yes.
this case it's only a linear combination, but we have like two coefficients for each vector in this case.
Yes.
B1 and B2.
Yes, here I'm putting it more explicitly. R is the residual that is always orthogonal to the space. So that's why it disappears and you don't get it in the formulas.
Okay, thank you.
For more dimensions, you can write the orthogonal projection to the space V of any vector y. Here I will not use colors, but let's say we have n vectors. You can always write it as vi, y, vi, vi, vi. This is the same as this one, so but with more terms, with more vectors, v1, v2, vn. So here our vector space V equals to the span of v1 until vn. Right. And what I wanted to show by doing this is another thing, that this residual here is actually, after doing this projection, the minimum residual possible. Why? Because if we have a space, now just V with n dimensions, and we have our vector y, and also P and R. If the length of R wasn't the smallest one possible, that would mean that the vector R would be a little bit tilted, and therefore the projection would not be orthogonal. Let me put it maybe as this. You can see that if the vector R is a little bit longer, that means that this angle is not 90 degrees. And if it's not 90 degrees, it's not an orthogonal projection. So to one side, it looks like this, but to the other side, it looks like this. So the minimum length only can be obtained when this vector R is orthogonal to the subspace. That means that this orthogonal projection can be written as a minimization problem in which we want to find coefficients. Let's say these coefficients are called alpha sub y. So a vector alpha. So the length or the norm of this R is minimum. This is an equivalent way of thinking to orthogonal projections. And why does it matter? Because this is exactly the formulation of a least squares problem. Why? Because this R can be written obviously as the thing that is lacking of the subspace, but we can write that as a matrix A that in each column has a vector V, this coefficients alpha minus y. Probably this is more familiar, but they are exactly the same. And that's the point that I wanted to show. Basically, after obtaining the orthogonal projection, you have the minimum of the residual after obtaining this vector P. P, by the way, here is this one, P, and the Y is that one, obviously. This one is Y. And this matrix A, just to be 100% clear, is a matrix that it has as columns the vectors v1 until vn. Right? So after multiplying by a matrix, a vector of coefficients alpha, you'll have exactly basically this. Alpha 1 times v1 plus alpha 2 times v2, and so on. So basically this would be P equals to alpha 1 v1 plus alpha 2 v2 plus blah 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 and vn. This is the same as the matrix vector product that I'm showing here. Okay. So here I'm saying exactly the same, but a very interesting thing is when our vectors are not only vectors, but they represent a signal. For example, here I have a noisy signal in blue that is represented by a vector of n dimensions, and we want to denoise this signal. This can be thought as well as projecting our noisy signals into a space that is represented by less noisy signals, right? So for example, here I'm creating the least squares problem with a matrix A, but this A is the space of polynomials that you are familiar now because you have seen it in the homework and in class in multiple times. So basically A is the function space of sampled polynomials. So in each column we have a polynomial of degree 0, 1, and so on. And by trying to fit a polynomial to a noisy signal, you can do a denoising. Here I'm showing what happens after I'm fitting the polynomials until degree 14 to this noisy signal. If I go, sorry, what happened? We need to run it again. If I go to the left, you see that the signal and the denoise signal match very well. If I start decreasing the degree of the polynomial more, until here, for example, I have a polynomial with degree 1. Here it says 3, but if I put 1 or 2, it would be the same. And basically, this 1 means until degree 0, just the way the function works, but this is a polynomial of degree 0, a constant. Then I have a linear function, and I start putting more and more coefficients, and you have a very good representation of the signal. Now, this is a double-edged sword, because if you put more coefficients than necessary, you start being very similar to the noise. And after some point, due to the noise, you actually have garbage. You start being very different from the noise, because you have too many degrees of freedom, and by trying to be similar to the noise, basically you get a very incorrect solution. You can see the same, for example, if you have a low degree polynomial and start putting more and more noise. You can see that after putting noise, the fitting of the function obviously also gets worse. Okay, are you following me with the example? This is an application of orthogonal projections to solve a least squares problem that in this case is doing a denoising of a signal. Yeah? Very good. Let me see the time. Okay, we have 5 minutes more. Right. Any doubts about this? This is just an application of orthogonal projections. But instead of just thinking of vectors, now our vector is a signal, and after projecting the signal onto the space of polynomials, in this case, we have a smoother signal. Okay, last thing I wanted to show is an example of a linear operator. To the other side. Okay, so this is a linear operator that is called the convolution between two signals. Here I'm just defining it as a operation between an input f and a predetermined filter or kernel. That's the way these h are called, to get a signal y. The intuition of the convolution is just the area after having one of those signals inverted and displaced. So if you move this h and get the result of the convolution in each point, here in red, start seeing when they meet each other, they start adding something. They start adding more and more and more linearly until they match, basically have a linear increase, and then it starts decaying linearly as well. Here I'm showing the convolution between two rectangular functions, and this gives the result of a triangular function. This can be compared to the roll of dice and the probabilities of obtaining a 7, for example. But we can talk about that in another tutorial. Okay, so a question, but obviously I have already responded the question, is that if the convolution is a linear operator, and that means that if I put instead of f1 plus alpha times f2, that will be the same as y1 plus alpha times y2. And here I will not show an example, but that is indeed correct. This operation is linear. You can kind of guess it by looking at the operation that is just a summation. So that's an intuition why it's linear, but you can do the proof by replacing this f with f1 plus alpha times f2 in a similar way of the exercise 1 of the homework 1. So yes, it's a linear operator. And let me show some examples of this operation, linear operation, that is called the convolution with a noisy signal. Here I am convolving this noisy signal in blue with this rectangular function. And what it's doing basically here is just adding up all these samples. And that is basically an average or a moving average of the signal. And when we have this type of convolution kernels, we have what it's called a low pass filter, that in this case is a moving average. So if we start from the beginning, we have a signal and we start averaging the values, and you can see that if we get all the values of the convolution, we have a smoother representation of the signal. If we, instead of that, we use a kernel that is with an abrupt change, basically what it will do is to have this right part subtracted from the left part. That is basically taking the derivative or the difference. So when we have the same signal, it's giving 0, but when we have an edge, it's giving something that is not 0, and the same for the other edge. And this type of filter is called high pass filter, and it's basically obtaining the details of a signal or an image. And another last thing that I wanted to talk with you is that when you apply a high pass filter to a very noisy signal, basically you are amplifying the noise. So it's not good to do this type of filters if you have a very noisy signal. Here you can see the solution that is bumps everywhere, so it would be very difficult to differentiate which parts comes from the noise and which ones comes from the signal. In this case, we can see that, or just because we are humans, we can see that the signal was like this, and obviously this peak is from the signal and this one as well, but for a computer this is not very easy to differentiate. Okay, so let's leave the recording until here, and we'll have a last round of questions in Spanish, but see you in the next TA. Bye, YouTube.